Okay, so the next thing we're going to do is show some things that'll come up commonly, maybe, or in some cases not so commonly, but will be useful ways of combining some of the different rules of inference and rules of equivalence that we've discussed in order to get things in a format that is easier to work with. All right. So first, making a conditional. So we can infer from the negation of a well-formed formula that the well-formed formula unnegated entails anything. So if we start with not s, we can get to if s then p, and we can do this by using addition to add or p to the not s. Remember, we know for certain not s, so uh, not s or p is going to be true because not s is true. So regardless of what we put as the other disjunct, this disjunction will always be true. And then we can go ahead and use material implication to get if s, then p. This might come up. It might not. I don't remember exactly if there's a proof that requires this in order to do, but something to keep in mind that you can do when you have something that's negated and you would like to turn it into a conditional that's unnegated using addition and then material implication like this is one way to do that. So this is an example of something that's not super intuitive, but given the rules of our system, totally possible. So something to keep in mind. All right. Next, any well-formed formula entails a formula that is already assumed or proven. So from S, we can conclude that if P, then S. And similarly, we can use addition to just add not P to S here. Then we could use commutativity to flip these around. S or not P is exactly the same as not P or S, so we can flip those. And then once we have them in this format, we can use material implication. And using material implication, we get if P, then S. Uh, so something that might come up using addition will allow you to go from just a static variable like this s here into these other relations with just the s. All right, switching antecedents of a nested conditional. So we can do this using exportation and commutativity. So if we have, in the first case, if p, then s, if p, then if s, then q, we can switch this around so that it reads if s, then if p, then q. Um, the end result here is going to be from P and S, we're going to get Q, but we'll walk through how to do that. So the first thing we'll do is use exportation to get that P and the S on one side as the antecedent of a conditional with Q as the consequent. You can probably imagine where things are going to go from here. Then we'll use commutativity to swap that S and the P. And then we'll use exportation again to get it back in the original format, but with the S and the P swapped. So we arrive at if S, then if P, then Q. Now, just because you know that this works, you can't just shortcut from 1 to 4. You would have to go through each one of these steps, even though some of them, like step 3, where you apply commutativity to step 2, are probably going to be really obvious to you. It's still important to uh, go through these one at a time and make it crystal clear to whoever's reading the proof how you got from one step to the next step. And in some cases, when you're applying something like commutativity, especially if it's to just a small part of a very long formula, to make it explicit what the rule is that you use, because sometimes it's not obvious at a glance, and so they can look for it. All right, next is negated conditionals. So from a negated conditional, it is possible to derive a conjunction using implication and De Morgan's, which can then be simplified. So if we have, it's not the case that if S then Q, and we want to show that S, well, the first thing we can do is take what's inside the parentheses and use material implication. So we go from if S then Q to not S or Q. Then we can go ahead and apply De Morgan's here. And remember, this is really important because the S on the inside of the parentheses, the first disjunct, was negated in the first place. When we apply De Morgan's, we're going to have two tildes, not just the one. It's important to remember that you always have to negate both of the disjuncts in this case, so we arrive at not S and not Q, which then gives us S and not Q. We can go ahead and simplify that to just S, and so we're able to get to just S, starting from it is not the case that if S, then Q. All right, here's something to be aware of. Because simplification is a rule of inference, it cannot be used on just part of a line. It's really important. If there's a bunch of stuff going on, and there's some conjunctions in the middle of a large, complex, well-formed formula, you can't just simplify out part of it. You can only use simplification when the conjunction is the main operator on that line that it appears. And then you can get, if it's the main operator on that line, there'll be two halves, and you can get the first of those halves onto a line by itself. Or you can use commutativity to swap them around and then get the other one on a line by itself. So in this example, if we start with if S then Q and P, and we try to simplify to just if S then Q, this doesn't work. This is a misapplication of the rule. This would be completely wrong. So watch out for that. But given that that's true, we can use implication, distribution, and simplification to end up with a similar result. So if we have if S then Q and P, and we want to show that if S then Q, we can go ahead and change this to a disjunction first by using material implication. So we change it to not S or Q and P. Then we can go ahead and apply distribution. So we change from not S or Q and P to either not S or Q and not S or P. And after using distribution, we can go ahead and simplify just one part of the first part that we want here, not S or Q. And from not S or Q, you're going to get probably pretty familiar with when you have a disjunct where the first disjunct, or disjunction where the first disjunct is negated, that's going to give us a conditional that we're looking for here, if S then Q. So we can get there using these rules, but it's really important that you can only use simplification in situations like line 3, where the conjunction is the major operator. All right. Next, we can reduce a conditional with a disjunction in the antecedent. So from S or Q, we can get to if S then P. We could also get to if Q then P, but we're going to do if S then P. And so the first thing we're going to do is use material implication. We're going to take the entire antecedent and negate it, and it'll be in a disjunction with the consequent as the other disjunct. Then from there, we can go ahead and apply De Morgan's. So we get, it's not the case that S and it's not the case that Q or P. We can use commutativity to swap these around, so we get the P up front. And then we can use distribution to get P or not S and P or not Q. And from here, we can go and simplify P or not S. We can use commutativity again to swap these back around, so we get not S or P. And from there, we get if S, then P. So intuitively, you can kind of tell that if S or Q, either S or Q are conditions for P being the case, well, it'll be true that if S then P and if Q then P, but this is a way to actually show it in a proof. All right, so we can also combine conditionals. So two conditionals that share an antecedent or consequent can be combined. This should be sort of intuitively obvious that if S then P and if S then Q, that if S holds that both P and Q are true, but here's a way to get there using our system. So first we'll use implication, material implication, to get not S or P. Then we'll do the same thing with line 2 to get not S or Q. Then we'll go ahead and use conjunction. We have not S or P and we have not S or Q. So it's true that we have not S or P and not S or Q. We can go ahead and put that on a line together as a conjunction. So that'll be 3 and 4 conjunction. And then we can use distribution on that line to get not S or P and Q. And from there, this is the format that we need to use material implication again. So we get if S, then P and Q. Pretty simple. Okay, next, if a statement entails its own negation, it is false. So with what we get to in a second, this will make more sense maybe. But if we have a statement like if S, then not S, well, then we can only conclude not S. Because if we use material implication on that, then we can see, well, either not S or not S. Which, using tautology, we can say, well, if we have two options, not S or not S, that's the same as there just being one option, in this case, not S. So we can get to just not S from if S, then not S. All right, so we're going to talk a little bit about the principle of explosion, which is something that happens if you end up with a contradiction somewhere in your proof. Now, we're not going to really have contradictions in our proof except in a later stage when we add another rule to our system here, in which case we'll be intentionally trying to get contradictions. But with the rules that have been given here, and in most classical logical systems, most classical logics, a contradiction entails anything. Anything follows from a contradiction. That's what's called the principle of explosion. So here, a contradiction is any statement of the form alpha and not alpha. So if we ever have something and its negation as being true, or we're assuming that they're true on different lines in our premise, then we can use addition to get anything out of that. So this is a little bit complicated here. But a real simple way to do it is if we have P and we have not P, then we can use the rule of addition to add absolutely anything we want to P. And because we have not P, then we can use disjunctive syllogism to get rid of the P and just say that whatever's on the other side of the P was true. So this is an example of how if something goes wrong and you end up with a contradiction, absolutely anything follows from it. So that's something that'll be useful. We're generally going to assume that you can't have a true contradiction. There are some logics that are set up such that there can be true contradictions, and there isn't the principle of explosion. If you're interested in this, you could look up dialectic logic. But most systems will work in such a way that there can't be true contradictions, and one of the reasons for that is that a true contradiction entails anything. It makes anything true. Okay, that's all for 3.5.